So we've accumulated some evidence that it might be possible to define division mod n. If a minus bq is congruent to 0 mod n, then a is congruent to bq mod n, and so we might say that a divided by b is q mod n. But how can we find q without repeated subtraction? We can look at division in another way. Division by b is the same as multiplying by the multiplicative inverse of b. So can we find a multiplicative inverse mod n? So remember, always seek the equation. The multiplicative inverse of b mod n will be some number x where bx is congruent to 1 mod n. So how can we find x? You could look up an algorithm for finding the inverse mod n. But so could someone else making half your salary. Remember, don't try to solve problems, create solutions. So let's see if we can find the inverse of 3 mod 7. So remember, when working mod n, you only need to work with the numbers between 0 and n minus 1, and trial and error always works. We want to solve 3x congruent to 1 mod 7, so let's try it out. So remember, if the modulus is understood, we can omit writing it. 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9, but we'll reduce that to 2, and so on. And we find that 3 times 5 is congruent to 1, so 5 is the multiplicative inverse of 3. Now, while this could work, it might take a lot of trial and error. So, for example, if we wanted to find the inverse of 11 mod 29, we find 11 times 1, 11 times 2, 11 times 3, and so on. Is there a faster way? So let's think about that. The pigeonhole principle is a useful idea in higher mathematics. If you have n objects and m less than n places to put them, at least 2 objects must be put in the same place. This is frequently used in number theory. Can we use it to find an inverse? Let's try it. To do so, we'll need to identify the objects, the pigeons, and where they're placed, the pigeonholes. So consider the sequence a squared, a to the 4th, and so on, formed by the fast powering algorithm. There's an infinite number of terms, but if we reduce these mod n, they can only be one of n values. So 2 of them have to have the same value. They have to be the same, giving us a to the p congruent to a to the q. Assuming that p is greater than q, this means we have, and this looks a lot like saying a to power p minus q is congruent to 1 mod n. So can we fast power to an inverse? Maybe. Let's find the inverse of 11 mod 29. So we'll use our fast powering algorithm to find 11. 11 squared is 121, which is congruent to 5 mod 29. 11 to the 4th is 11 squared squared, that's 5 squared, or 25. 11 to the 8th is 11 to the 4th squared, 25 squared, which is 625, which we can reduce down to 16. 11 to the 16th will be 11 to the 32nd will be, and notice, as promised, we have 2 powers that are the same. And so we have 11 to the 32nd must be congruent to 11 to the 4th. So if we reduce both sides, we'll get 11 to the 28th congruent to 1 mod 29, and that says that 11 times 11 to the 27th is congruent to 1. And note that we can find 11 to the 27th. We've already done all the work needed to find it. That's 11 to the 16th times 11 to the 8th times 11 squared times 11. And that will be and we see that 11 times 8 is 88, which is in fact congruent to 1 mod 29. So this seems to work to find inverses. But remember, if you don't find your mistakes, someone else will. So let's try to use this approach to find the inverse of 8 mod 12. So we'll go through the same steps. 8 is congruent to 8. 8 squared is 64, which is congruent to 4 mod 12. 8 to the 4th is also 4. So 8 to the 4th is congruent to 8 squared, which suggests that 8 squared is 1. Since this means 8 times 8 is congruent to 1, then 8 is its own inverse. Except when we check it, we find that 8 times 8 is, well, that's just 8 squared, and we already determined that was congruent to 4. So what happened? We'll take a look at that next.